Welcome to this problem-solving session. In today's video, we'll tackle problem number 1306, Jump Game 3. This problem involves determining if it's possible to reach any index with a value of 0, starting from a specified index in an array by jumping forward or backward. Let's dive in and explore the solution. In this problem, you are given an integer array called ARR and a starting index start. Your goal is to determine if it is possible to reach any index in the array where the value is 0. At each step, you can jump to the left or right by the value at your current position in the array. Importantly, you cannot jump outside the bounds of the array, so your jumps must stay within the valid range of indices. The function should return true if you can reach an index with the value 0, and false otherwise. The input consists of two parts, RR, which is a list of integers with a length between 1 and 50,000, and start, which is the initial index in the array, ensuring that start is always within bounds. The output is a Boolean value indicating whether it's possible to reach any 0 in the array by following the allowed jumping rules. Let's take a look at some examples to better understand this problem. In the first example, the input array is 4, 2, 3, 0, 3, 1, 2, and the starting index is 5. The output is true, meaning it is possible to reach an index with the value 0. Here's how: starting at index 5, which has the value 1, you can jump to index 6. From index 6, which has the value 2, you can jump to index 4. At index 4, the value is 3, and jumping from here leads you to index 3, where the value is 0. Since we've reached an index with the value 0, the output is true for this example. Now for the second example, the input array remains 4, 2, 3, 0, 3, 1, 2, but the starting index is 0. The output is still true, and here's why: starting at index 0, which has the value 4, you can jump directly to index 4. From index 4, with a value of 3, you can jump to index 3, where the value is 0. Once again, we've successfully reached an index with the value 0, so the function returns true. Let's consider one more example to see how the output can also be false. In the third example, the input array is 3, 0, 2, 1, 2, and the starting index is 2. The output is false, as there is no way to reach an index with the value 0 from index 2. Here's what happens: starting at index 2, the value is 2, so you can jump either to index 4 or back to index 0. However, from either index 0 or index 4, none of the subsequent jumps will lead to index 1, which is the only index with the value 0. To solve this problem, you must also consider the constraints. The array length can be as large as 50,000, and each element can be up to 10,000. Additionally, you must account for edge cases, such as when the starting index already has a value of 0, or when all elements in the array are non-zero, making it impossible to reach any index with the value 0. Efficient handling of circular or repeated jumps is critical to avoid infinite loops in your implementation. In the problem Jump Game 3, the goal is to determine if you can reach any index in the array ARR where the value is 0, starting from a given start index. From any index I, you can jump forward by ARR I steps or backward by ARR I steps. However, there are some constraints: you cannot jump outside the bounds of the array, and you cannot revisit indices you've already visited. To solve this, we can think of the problem as a graph traversal task. Here, each index acts as a node, and the possible jumps define the edges connecting these nodes. A key consideration is that revisiting indices can create cycles, which may lead to infinite loops. Therefore, it's critical to track which indices have already been visited. Finally, the search process ends successfully as soon as we find an index with the value 0, which acts as our termination condition. One potential way to solve this problem is through a brute force approach, which involves an exhaustive search. The idea is to explore all possible paths starting from the start index and check every reachable index. This can be implemented either recursively or iteratively by simulating jumps in both forward and backward directions. However, the brute force approach is highly inefficient. The time complexity is exponential, specifically O(2 to the power of n), because each index can lead to 2 new jumps. The space complexity is O(n), due to the recursion stack if we use a depth-first search approach. While this method is conceptually simple, its exponential growth makes it impractical for large arrays, such as those with n up to 10 to the power of 4. This inefficiency is a major limitation of the brute force method. A more efficient strategy is to use breadth-first search, or BFS. The intuition behind BFS is to explore the indices level by level, systematically checking all reachable indices. This can be implemented using a queue to store indices that need to be explored, while a visited set is used to track indices that have already been processed, preventing redundant work. The time complexity of BFS is O(n), as each index is visited at most once. The space complexity is also O(n), to account for the queue and the visited set. BFS has several advantages. It ensures systematic exploration, which makes it easier to reason about the solution. It also avoids the risks of stack overflow that can occur with recursion in DFS. However, BFS does require explicit memory management for the queue and visited set. Additionally, we can consider depth-first search, or DFS, as an alternative. In DFS, paths are explored deeply before backtracking. This can be implemented using either recursion or an explicit stack, and it also requires tracking visited indices. Like BFS, DFS has a time complexity of O(n), with space complexity of O(n), due to the recursion stack or stack data structure. DFS is simpler to implement but comes with the risk of stack overflow for large input sizes. For this problem, we chose breadth-first search, or BFS, as the optimal approach. BFS offers several advantages that make it well-suited to this task. First, it ensures systematic exploration, making the solution easier to debug and reason through. Second, unlike DFS, BFS avoids the risk of stack overflow, which can occur with deep recursion on large input arrays. Additionally, BFS guarantees finding the shortest path to a solution, though path length isn't a critical factor here since we only care about reaching A0. There are a few trade-offs to consider. BFS requires maintaining an explicit queue, which may involve more memory management compared to the implicit recursion stack used in DFS. While DFS is slightly simpler to implement, BFS is ultimately more robust for handling problems with large input sizes, making it the preferred choice for this scenario. To implement the BFS solution, we start by initializing a queue with the start index and a visited set to track indices that have already been explored. While the queue is not empty, we dequeue an index I to process it. If the value at ARR I is 0, we return true, as we've reached a valid solution. Otherwise, we calculate the forward jump to I plus ARR I, and the backward jump to I ARR I. If these indices are within the bounds of the array and have not yet been visited, we add them to the queue and mark them as visited. This process continues until either a solution is found or the queue is exhausted. If the queue is emptied without finding a 0, we return false. The time complexity of this algorithm is O(n), as each index is visited at most once. The space complexity is also O(n), accounting for the queue and visited set. This ensures an efficient and systematic solution to the problem. The problem jump game 3 challenges us to determine whether we can reach any index in an array ARR that has a value of 0, starting from a given index start. From any index I, you can jump forward to I plus ARR I, or backward to I ARR I, as long as the destination index remains within the bounds of the array and hasn't already been visited. To solve this, we can use graph traversal techniques by visualizing the array as a graph where each index is a node and the jumps represent the edges connecting these nodes. The approach we'll focus on here is breadth-first search, or BFS. To begin, we initialize a queue, which will help us systematically explore the possible jumps, starting with the given start index. Additionally, we use a visited set to keep track of indices we've already processed, ensuring we don't revisit them and create cycles. Next, we start the BFS traversal. While the queue is not empty, we dequeue the current index I to process it. The first thing to check is whether ARR I equals 0. If it does, we've successfully found a path to a 0, and we return true. If not, we compute the possible jumps from I. To jump forward, we calculate forward equals I plus ARR I. If this index is within bounds and hasn't been visited yet, we unqueue it and mark it as visited. Similarly, to jump backward, we calculate backward equals I ARR I. If this index is also valid and unvisited, we unqueue it and mark it as visited. The process continues until either we find a 0 or the queue is exhausted. If the queue is empty and we haven't found any index with 0, we return false, as no valid path exists. Now, let's discuss some key insights. First, why do we use BFS? BFS is ideal for this problem because it explores all indices level by level, or jump by jump, ensuring that the shortest possible path to an index with 0 is found if it exists. Another critical component is the visited set, which prevents revisiting indices. Without this, it's possible to end up in infinite loops, especially in situations where the jumps repeatedly move back and forth between the same indices. Additionally, there are important edge cases to consider. For example, if the value at ARR start is already 0, we can immediately return true without any traversal. On the other hand, if the start index is out of bounds, the answer is false. Arrays with all positive or all negative values can also create situations where certain indices are unreachable. Finally, the algorithm's time complexity is O(n), where n is the size of the array, because each index is encoded and decoded at most once. Operations like checking bounds or marking indices as visited take constant time, making the approach efficient. In terms of space complexity, the visited set and the queue together require O(n) space in the worst case, where n is the size of the array. This is because, in the worst scenario, we may need to store all indices in the queue and the visited set. The two primary data structures used here are the queue and the visited set. The queue is essential for the BFS traversal, ensuring that indices are explored in the correct order, level by level. The visited set, on the other hand, is crucial for tracking indices that have already been processed. This prevents unnecessary cycles and redundant computations, ensuring the algorithm remains efficient. Let's walk through an example to solidify our understanding. Consider the input array ARR equals 4, 2, 3, 0, 3, 1, 2, and the starting index start equals 5. We begin by enqueuing the index 5 and marking it as visited. Dequeuing 5, we check if ARR 5 equals 0. Since it doesn't, we calculate the possible jumps. Jumping forward gives 5 plus ARR 5 equals 6, so we enqueue 6 and mark it as visited. Jumping backward gives 5 ARR 5 equals 4, so we enqueue 4 and mark it as visited. Next, we process index 6. Here, ARR 6 is not 0. Jumping forward to 6 plus ARR 6 equals 8 is out of bounds, and jumping backward to 6 ARR 6 equals 4 leads to an already visited index, so no new nodes are added. Then, we process index 4. Again, ARR 4 is not 0. Jumping forward gives 4 plus ARR 4 equals 7, which is out of bounds, and jumping backward gives 4 ARR 4 equals 1, so we enqueue 1 and mark it as visited. Finally, we process index 1. Here, ARR 1 is not 0. Jumping forward gives 1 plus ARR 1 equals 3, so we enqueue 3 and mark it as visited. Jumping backward gives 1 ARR 1 equals -1, which is out of bounds. Now, we process index 3. At this point, we find that ARR 3 equals 0, so we return true. This example demonstrates how BFS systematically explores all possible paths until a valid solution is found. The output for this input is true, indicating that it is indeed possible to reach an index with 0 starting from the given index. Here, we start by importing the necessary module, deq, from the collections library. This will help us perform a breadth-first search, or BFS, which is the strategy we'll use to solve the problem. Inside the solution class, we define the canReach method that takes two inputs, the array ARR and the starting index start. First, we calculate the length of the array and initialize a visited list with false for each index to track whether we've already visited a position. This prevents infinite loops during traversal. Next, we set up a queue and initialize it with the starting index. The queue will help us process each position level by level. Inside the while loop, we repeatedly dequeue an element, which represents the current index we're processing. If the value at this index is 0, we immediately return true because we've found a valid path to a 0. If not, we mark the current index as visited to ensure we don't revisit it. Then, we calculate the forward jump by adding the value at the current index to the index itself. If the resulting position is within bounds and hasn't been visited yet, we add it to the queue for future processing. Similarly, we calculate the backward jump by subtracting the value at the current index from the index itself. If this backward position is within bounds and hasn't been visited yet, we enqueue it as well. By continuing this process, the algorithm explores all possible paths from the starting point using BFS. If the loop completes without finding a zero, we return false, indicating that no valid path to a zero exists. This approach ensures that we systematically explore all reachable indices and avoid revisiting positions, making the solution both efficient and correct. Here, we start by importing the necessary libraries and defining our solution class. The main method we're focusing on is canReach, which takes an array ARR representing the game board and an integer start, which is the index we begin from. The first thing we do is determine the length of the array and create a visited array to keep track of which indices we've already checked. This prevents us from revisiting the same indices and getting stuck in an infinite loop. Next, we initialize a queue for our breadth-first search, or BFS. BFS is a great choice here because it systematically explores all possible paths from the starting point. We add the starting index to our queue and begin processing it in the while loop. Inside the loop, we dequeue the current index we're examining. If the value at this index is 0, we've reached our goal, so we immediately return true. If not, we mark the current index as visited to ensure we don't revisit it. The next steps involve calculating the indices we can jump to. First, we calculate the forward jump by adding the value at the current index to the index itself. We then check if this forward index is within bounds, hasn't been visited, and is a valid move. If it is, we add it to the queue to explore later. We then handle the backward jump in a similar way. This time, instead of adding the value at the current index, we subtract it to move backwards on the game board. Again, we check if this backward index is within the boundaries of the array, hasn't been visited, and is a valid move. If all these conditions are met, we add it to the queue for further exploration. The BFS loop ensures that we systematically explore all reachable indices, both forward and backward, until we either find a zero or exhaust all possible paths. If the queue becomes empty and we haven't returned true, it means there's no way to reach an index with a value of 0 from the starting point. In that case, we return false. This approach ensures that we thoroughly explore the board while avoiding infinite loops, thanks to the visited array, and it efficiently checks all possible paths using the BFS strategy. Let's analyze the first example where the input array is 42303112, and we start at index 5. We initialize our queue with the starting index, so q equals dec 5, and our visited list has all values set to false initially. Dequeuing index 5 gives us the value 1, so we mark index 5 as visited. Now, we calculate two potential moves, forward to index 6, which is within bounds and not visited, and backward to index 4, which also satisfies these conditions. Both indices are added to the queue, so the updated queue is dec 6, 4. Next, we dequeue index 6, where the value is 2. Marking index 6 as visited, we calculate forward to index 8, which is out of bounds, and backward to index 4, but it's already visited. Thus, only index 4 remains in the queue. Dequeuing index 4, we find the value 3. After marking it as visited, forward moves to index 7, which is out of bounds, and backward moves to index 1, which is unvisited, so we enqueue index 1. Now the queue contains only index 1. Dequeuing index 1 reveals the value 2. We mark index 1 as visited and calculate a forward move to index 3, which hasn't been visited yet, so it's enqueued. The backward calculation results in index -1, which is out of bounds and hence ignored. The queue now holds index 3. Dequeuing index 3, we find the value 0, which is our target. Since we've reached a 0, we return true. This concludes the first example, as we've demonstrated that it's possible to find a path to a 0 starting from the given index. In the second example, the input array is 3641250, and we start at index 0. The queue is initialized with dec 0, and the visited list is all false. Dequeuing index 0 gives a value of 3. We mark index 0 as visited and calculate forward to index 3, which is unvisited, so we enqueue it. The backward move to index -3 is out of bounds. Now the queue contains index 3. Dequeuing index 3 reveals the value 1. We mark index 3 as visited, calculate forward to index 4, and enqueue it since it's unvisited. Backward to index 2 is also a valid unvisited move, so we enqueue index 2 as well. The queue now holds indices 4 and 2. Dequeuing index 4, the value is 2. Marking it as visited, we calculate forward to index 6, which is unvisited, and enqueue it. Backward to index 2 is already visited, so the queue updates to dec 2, 6. Next, we dequeue index 2, where the value is 4. After marking index 2 as visited, the forward calculation moves to index 6, which has already been visited, and the backward calculation to index -2 is out of bounds. This leaves index 6 in the queue. Dequeuing index 6, we find the value 0, which means we've successfully reached our target. Thus, we return true. In this example, we've again demonstrated that it's possible to find a path to a 0 starting from the specified index. In the third example, the array contains only one element, 1, and the starting index is 0. The queue is initialized with dec 0, and the visited list contains a single false value. Dequeuing index 0 gives the value 1, so we mark index 0 as visited. Calculating forward moves to index 1, which is out of bounds, while backward moves to index -1, which is also out of bounds. With no further indices to explore, the queue becomes empty. Since we've exhausted all possibilities without finding a 0, we return false. This example illustrates that it's not always possible to reach a 0, particularly when the array lacks 1 entirely. To analyze the time complexity of our solution for Jump Game 3, we start by breaking it into two main components, initialization and the BFS traversal. During initialization, we create a visited array with n elements, all set to false. This operation requires O(n) time since we have to iterate through the entire array. Additionally, the queue is initialized with just the starting index, which is a constant time operation, O(1). Now, when we move into the BFS traversal, we process each index in the array. In the worst case, every index will be added to the queue and later dequeued exactly once. This results in a total of O(n) queue operations. For each index dequeued, the algorithm calculates two potential jumps, one forward and one backward. These calculations are constant time operations, O(1), so the total amount of work per index is also O(1). Since there are at most n indices, the BFS traversal contributes O(n) to the overall time complexity. When we combine this with the initialization cost, the total time complexity of the algorithm is O(n). Now let's look at the space complexity. The first major component of space usage is the visited array. This array has a Boolean value for each index, which ensures no index is revisited during the BFS traversal. Since the input array has n elements, the visited array requires O(n) space. The second component is the queue used in the BFS. In the worst-case scenario, all n indices could be added to the queue simultaneously, which means the queue would require O(n) space as well. Beyond these two structures, there is no additional significant auxiliary space used in the algorithm. Therefore, when we combine the space used by the visited array and the queue, the total space complexity of the algorithm is O(n). Next, we analyze the algorithm's behavior in the best, average, and worst cases. In the best case, the starting index already points to a value of 0. As a result, the algorithm terminates immediately with no need for traversal, leading to a time complexity of O(1) and a space complexity of O(1). In the average case, the BFS explores a portion of the indices before reaching an index with a value of 0. On average, this results in O(n) time and O(n) space, as the BFS still requires the use of the visited array in the queue. Finally, in the worst case, the BFS must traverse all n indices in the array before determining whether or not it can reach an index with a value of 0. This worst-case scenario results in O(n) time and O(n) space as well. Comparing the brute force approach to the optimized BFS solution highlights the efficiency of our algorithm. A naive solution would involve recursively exploring all possible paths from the starting index. Since each index has two potential jumps, forward and backward, this results in an exponential time complexity of O(2 to the power of n), which becomes infeasible for large input sizes. Additionally, the recursion stack in the brute force approach would require O(n) space. On the other hand, the optimized BFS solution ensures that each index is processed at most once, reducing the time complexity to O(n). By using the visited array, it avoids redundant computations and ensures efficient traversal. The BFS approach also maintains a space complexity of O(n), primarily due to the visited array and the queue. Overall, the optimized BFS is highly efficient and well-suited for solving jump game 3, providing a significant improvement over the naive approach, especially for larger arrays. When tackling this problem, there are several common mistakes to watch out for. First, it's easy to overlook index bounds when calculating jump positions. If you attempt to jump to I plus ARR, I, or I ARR, I, without ensuring the new index is within the array bounds, your program could crash. To avoid this, always validate that the calculated index is between 0 and len, ARR, 1 before proceeding. Another mistake is revisiting indices unnecessarily, which can lead to infinite loops or wasted processing. To prevent this, use a visited set or modify the array to mark indices that have already been processed. However, be cautious when modifying the input array. Some solutions overwrite values with 0, which can interfere with the logic since 0 is the target value. Instead, use a unique placeholder like -1 that doesn't conflict with valid values. Finally, make sure to explore both directions, jumping forward and backward. Forgetting one direction can result in incomplete paths and incorrect solutions. Inefficient traversal is another challenge you may face. Brute force or recursive DFS without memoization can lead to redundant calculations and even timeout errors for larger inputs. To address this, opt for BFS or an iterative DFS approach. BFS is particularly suited for exploring the shortest path to a solution, while iterative DFS avoids stack overflow issues. Now, in terms of interview insights, it's helpful to think of this problem as a graph traversal. Each index in the array can be treated as a node, and jumps represent edges between nodes. Efficient traversal strategies, like BFS, allow you to handle large arrays, sometimes up to 10 to the power of 4 elements, by ensuring early exits when a solution is found. Additionally, the problem has parallels to cycle detection in graphs, so marking nodes as visited is crucial to avoid redundant processing. Be prepared for follow-up questions, such as finding the minimum number of jumps to reach a 0 or handling arrays with negative values. Adapting BFS to track jump counts is a common way to extend the problem. This problem shares similarities with other problems, which can deepen your understanding of traversal techniques. For instance, problem 55, jump game, asks whether you can reach the last index of the array, while problem 45, jump game 2, focuses on finding the minimum number of jumps needed to get to the last index. Both problems emphasize reachability and optimal pathfinding. Jump game 3, the problem we're discussing, builds on these ideas by adding bidirectional jumps and a specific target value of 0. Then there are problems like number of enclaves, which uses similar traversal logic but in a grid instead of a 1D array. Finally, rotting oranges is a BFS-based problem that also involves state propagation, where you explore all connected components level by level. Familiarity with these related problems can help you recognize patterns and apply the appropriate traversal techniques effectively. To solve jump game 3, there are 3 main approaches you can consider. First, breadth-first search, or BFS, uses a queue to explore all reachable indices level by level. This approach ensures that you process each index only once and prevents cycles by marking indices as visited. While BFS is efficient, it does require additional space for the queue and visited structure. Next, there's depth-first search, or DFS. This can be implemented recursively or iteratively to explore paths deeply before backtracking. Like BFS, you should mark indices as visited to avoid revisiting them. Recursive DFS, however, can lead to stack overflow for large inputs, so an iterative version might be more reliable. Lastly, you can use in-place modification by marking visited indices directly in the array, setting them to a placeholder value like -1. This approach minimizes space usage but comes with the trade-off of modifying the input, which might not be acceptable in all scenarios. Each method has its strengths and trade-offs, so choose the one that best fits the constraints of your problem. Great job making it to the end. Today, we explored jump game 3, a problem that tests graph traversal skills like DFS and BFS. Remember to practice using these techniques in similar problems to strengthen your understanding. Thank you for watching, and don't forget to like and subscribe for more coding tutorials. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!